on to H. Okay, applications of differentiation of log e of x. So this is where we find tangents and normals and the like. Okay, so straight into the questions. Number 1, show that the tangent to y equals ln of x at the point t, which is E1, has the equation x equals EY. We actually know what the answer is we've got to get to. We've got to get to that x equals EY. Okay, but we can't use it. We've got to start from scratch. So we are starting with y equals ln of x. It's a tangent that I'm after, so I have to differentiate. The derivative is 1 over x. Good. Okay, I want the gradient at this point that I've been given, which is when x is equal to e. So I'm going to sub that in. When x equals e, my derivative will be 1 over e. Okay, now to find the equation of my tangent, I will use y minus y1 equals mx minus x1. I have a point, and I've just found a gradient, so I'm using my point gradient formula. Okay, so subbing in y take away 1 equals gradient was 1 over e, x take away e. Expanding my bracket, y take away 1 equals 1 over e times x would be x over e. 1 over e times minus e is? Say what? Not quite. Negative 1, because the e's will cancel out. You've got an e on the top, e on the bottom. Negative 1. Now, look at this. Minus 1, minus 1. If you add 1 to both sides, these disappear. Okay, so we have y equals x over e. If you times the e over to the other side, you get x equals ey, which is what we wanted. Done. All right, part B. Find the equation of the normal, still of y equals ln of x, and my point t, which is E1. I'm not starting from nothing. This is flowing on from part A. I already know that my first gradient is 1 over e. That's the gradient of my tangent. We worked that out already. So because this is a normal, M2 is the negative reciprocal, which is, what will it be? Negative e. Okay. And we're still going through that point, t equals E1. So we're using this gradient, this point, and we're finding the equation again with y minus y1 equals mx minus x1. So y minus 1 equals minus e, x minus e. Let me expand it out. Y minus 1 equals minus ex plus e squared. And just add your 1 over. Y equals minus ex plus e squared plus 1. Now, often when you see these answers in textbooks, for example, they might put that part in brackets just to help you see if this is the y equals mx plus that whole thing is my y-intercept. It's just that it's 2 terms because it's an e with a constant, with a number. Yeah? Okay, part C. Sketch the curve, the tangent, and the normal, and find the area of the triangle formed by the y-axis, the tangent, and the normal at t. Okay, why not? All right. So let's draw our logarithm. Y equals ln of x. That's the standard logarithm, no movement, which means my vertical asymptote is at x equals 0. Battery's dying. Oh no, plugging in. Okay. Then, where is my x-intercept? Silence. 1. Remember? 1. Okay. Then, we know the shape is going to be coming around like this. But there's probably at least one other point we should show, which is the point T. Yes? Because that's the point this is all about. So the point T was E1. I'm going to put E there, which means 1 will be there. This is my point T. Okay, so we want to show the tangent. Now, let's have a look back. The equation of my tangent in the light blue here was x equals EY. What do you know about that graph? That's positive gradient, yes. What point is it going through that's very significant? The origin. Yeah, the E is like it's a constant, it's a number, it's 2.7, whatever, okay? But there's no plus number there. There's no extra y-intercept, which means it's going through the origin, yeah? So my tangent, when I draw it, I need to make sure, if I fudge it a little, that it's going through the origin. Does that almost look right, hopefully? So there's my tangent. Make my dot a little bit bigger to make sure they look like they touch. Okay, maybe I shouldn't do that. That's a bit dodgy, but anyway, make sure yours looks right. Then I want to do the normal, and depends how much room you've got. This is going to go way high. I'm going to have to make mine look not quite so right angular, I think. Okay, so this is a right angle, even though it doesn't look like a right angle. Otherwise, my triangle would go too high. Okay, so what do I know about my normal that I can put on my graph here? The y-intercept. I think you said it, Tyler, right? So that e squared plus 1, remember I talked about it before? That's the y-intercept. That's up here. That number there would be e squared plus 1. All right. Have I got everything I need? Sketch the curve. Find the area of the triangle formed by the y-axis, the tangent, and the normal. So I'm after this area in here. I know the height, the e squared plus 1. I know this height here. Yeah. The height of the triangle that way would be e. So if we think of the triangle as being on the side, if the e squared plus 1 is the base, and that red dotted line that I've drawn is my perpendicular height. Yeah? So I can do A for area, or right area, equals half base times height. So it'll be half times my base, which is e squared plus 1, and my height, which was e. So probably move the e to the front. Looks a bit better there, but that's it. There's my area. Yes, I guess it would be units squared as well. You need to go? Okay. All right, on to the next one, question 2. Write down the domain of y equals x log e of x. All right, we know the domain of log e of x, right? What is it? X must be greater than 0. If I times it with x, what does that change? Nothing. Because log will only exist when x is greater than 0, timesing it by x means that it still has to be that x is greater than 0. Yeah, the x at the front, I could have other values, but because I can't have it for the logarithm, I can't have it for the whole thing. Yeah? So my domain is going to be x is greater than 0. If you want to write a little note as to why, it's because log e of x is undefined when or for x is less than or equal to 0. Which means if you're trying x times by something undefined, you can't do it. So it doesn't exist there. Okay, which is why x has to be greater than 0. Part B. Test whether y equals x log e of x is even or odd or neither. Okay, that's a bit of a trick question. What would we normally do to test if something is an odd or an even function? Sub in negative x. But there's a problem. Our logarithm does not exist for negative values. We've just talked about that in part A. So if it doesn't exist for negative values, I can't have a part of a graph down here being reflected, right? Okay, so what does that mean? It's neither. It can't be even or odd because there's going to be nothing on that left-hand side of the graph. Yeah? So we're just going to have to say neither, since x is undefined, same reason as before, undefined when x is less than or equal to 0. Okay, can't sub in that negative x. It doesn't exist. Part C. Find any zeros of the function and examine its sign. Zeros, intercepts, which is when y equals 0. That's my intercepts, my x-intercepts. That would mean that 0 equals x log e of x. What are my solutions to that equation? Null factor. Null factor. There's two things times there. Either the x equals 0 or the log e of x equals 0. However, can x equal 0? No. So this one's a big fat no, because yet again, x has to be greater than 0. Okay, so it can't be equal to 0. It has to be greater than 0. What about the other one? Slide the base. X equals e to the 0, which means that that's x equals 1. All right, so I have found one. There is a 0, okay, which is at x equals 1. That's my normal, just for the log e of x, that's my normal intercept, right? So it's the same thing. Now, examine its sign with a sign table. Okay, sign table. We have x, we have y, and we want to see what is happening to the sign. Okay. I made it, when I did this table, I thought it might be prudent to put 0 there, just to show it doesn't exist here. There is my vertical asymptote. Don't try and pick anything less than 0. Doesn't exist. Okay? My value here is at 1, which means most people would go, let's sub in 0. No, it doesn't exist there. Okay? So I'm going to have to choose something like a half. Okay, but on the other side we're fine. We can do 2 on the other side. Yeah? All right, so if we sub in 1, we know that that's our 0. When we sub in a half, so you grab your calculators out and you type in half log e of half, and you get, what was it, Grace? Yeah, so negative 0.3, that's enough. All I need to know is that it's negative. Okay, type in 2 log e of 2. I got 1.4. Yeah, so all we need to know there is that it's positive. So negative 0 positive, this, anyway, it's negative, sorry, it's not a turning point. It's negative on the left side of the turning point, coming up, and positive on the other side. Part D. This is the one where I want the turning points. No, not yet. That's part E. Getting ahead of myself. Part D. Examine the function's behavior as we go to infinity and negative infinity. Noting any asymptotes, you may assume that x log e of x is approaching 0 as x is approaching 0 because all right, so we want to find out from our hint as y is approaching 0. Now y is the x log e of x, right? That means that my x value my x values are approaching 0. That was what it said in the hint. Also, what happens as we go to infinity? As x is approaching infinity, let's think about this. Log e of x, which one's dominant over that? So the x or the log e of x? Which one's going to have all the power out of that multiply there? The x. Log e of x, because you're saying which one is increasing the fastest, right? So when it's an exponential, the exponential takes over because they increase super fast. But a logarithm, it's coming up, but it starts coming up really slowly. The further you go out here, it's barely increasing at all. Super slow increase. Okay? So when you're multiplying it with x, and x is approaching infinity, that x out the front, it's got all the control. It's doing all the work, okay? So if x is approaching infinity, x log e of x is approaching infinity as well. So the y value is approaching infinity. And we have to say it, if x is approaching negative infinity, don't be an idiot. Can x approach negative infinity? No. X is always greater than 0. It said it in the question that I have to say it because it said, what's happening as x approaches negative infinity? But we've said it like 3 times in this question. Can't happen because x must be positive. They're trying to trick us. Yes?
It's moving that way.
It's approaching, when it's approaching the asymptote, it would be approaching negative infinity. We're not approaching the asymptote. We're trying to go out to negative infinity for the x value, which we can't do. No, it's not the same. Not the same. That's why I did the one at the front here, because 0 is my asymptote. Anyway. All right, part E. Find any stationary points and examine their nature. Stationary points are when the derivative equals 0, but this is a product because it's x log e of x, right? So we're going to have u equals x, v equals log e of x, u dash equals 1, v dash equals 1 over x. Okay, so using the product rule, y dash equals VUV. We're doing v times u dash, so that would just be log e of x, plus x times 1 over x. It's just 1. X's cancel. Yeah? Now we're going to say, because we want stationary points, I want my derivative equal to 0. So that means log e of x, I'm going to move the 1 across, so equals minus 1. Slide the base. x equals e to the negative 1. Or 1 over e if you prefer the fraction. Same deal. So I have to find a stationary point. I have found a stationary x value. How do I find a stationary y value? Sub it back into the original equation. So y is x log e of x. So it's e to the negative 1 log base e of e to the negative 1. Okay, so what do I do with that log base e of e to the negative 1? The power. The power is going to come down the front, like that. And then the log e of e is 1. Gone. So there's my y value, or you could change it into fraction, if you like. So that means that my stationary point, what was my x value? My x value was 1 over e, and my y value was negative 1 over e. Still not done, because it says find any stationary points, done that, but now I have to examine their nature. Their nature. So maximum or minimums. You can do a table, but most of the time, if it's easy to differentiate, I like to differentiate the second derivative. I find it faster. It's up to you, though. I've seen plenty of you guys on the test that seem to prefer the table. If you like the table, do the table. Okay? All right, so second derivative. Remember my first derivative is right here, y dash. There it is. So differentiating log e of x, you get 1 over x. The 1, gone. So there's my second derivative. All I have to do is sub in that x is equal to the 1 over e. So my y double dash would be 1 over e. Do you want me to write that down? 1 over e. Or in other words, e, because it's the reciprocal. Now, e is a positive number. That's all we really care about. It's greater than 0, which means that it's a what? A maximum or a minimum? Minimum. All right, we have done that. Next, getting close to the end, f. F, find any points of inflection and examine the concavity. Points of inflection are when we make the second derivative equal to 0. My second derivative was 1 over x. Can 1 over x be equal to 0? No. Because as soon as you try and times that x over, you get 0 equals 1. So this has no solution. So that must mean, let's have a look at our y double dash equals 1 over x a bit more thoroughly, since we can't use our second derivative like we normally would. Knowing that x has to be greater than 0. Yes, x is always greater than 0. So no matter what x value that is greater than 0 that I put in there, my second derivative is always going to be positive. Okay? So that must always be greater than 0 because my x has to always be greater than 0. Okay, so not very traditional, but we're still getting there. So if my second derivative is greater than 0, I don't have a point of inflection, so I couldn't find one, but I do know about the concavity. If the concavity is positive, what does that mean? Concave up. This whatever this thing is always concave up. So therefore, no point of inflection because we couldn't solve for the second derivative, but the curve is always concave up. Now, with all of this lovely analysis, hopefully we can finally sketch our graph. All right. Big graph. Now, there's no negative x values. Okay, just putting it out there. You don't need much on the left. There's nothing over there. Okay, we found a turning point. Where was it? Yeah. Now, did we also find an intercept? Yeah, right back at the beginning, part C. The 0, x equals 1. So at x equals 1, there's my x-intercept. I have a turning point, 1 over e, as an x value. It's about a half. 1 divided by e. It's 0.37. Yeah, anyway, close enough. It's going to be down here. Because negative 1 over e would be the negative version. So this point here is 1 over e, negative 1 over e. It is never, that is a minimum turning point we found. It's never going to hit the origin. So it's going to come down. Oh, sorry, curvy, more curvy. Like that. Always concave up. Always concave up. Yeah, so that's what it looks like. No, because x has to be greater than 0, can't be equal to 0. So that's why I open circle, because it can't be at that point. But it is approaching the 0, because we did discuss back here that as x is approaching 0, y was approaching 0. Anyway, that was quite an involved question. You can now do 6H. It's not an asymptote, it's a discontinuous